So, do you have any questions or clarifications from what we did last time? Okay. So, there are a couple of topics that I want to talk about. They are in 3 different pieces. So, the first one is smoothing, and this is sometimes very important, as you would see. The reference that I am using is from David Chack and Laird, and this is a simulation of a hot sphere crystal melt interface from 1998. And if you go to the paper, the abstract proudly says that they have 10 power 4 hot spheres in their model for the simulation. And this is where some of these early things were set, and one of the things that this paper gets referred to is for identifying a process to smooth the profiles. And there is a master's thesis from McMaster, Jeff Hoyt's student, and they have done molecular dynamic study of solid liquid interface properties. Yesterday I showed you for iron, which is BCC, and Mishin and Frollo had done for lots of FCC, and this is HCP. And this thesis also explains in little bit of detail whatever is there in David Chack and Laird, but at least one figure was very useful for us, which made us follow this process fairly easily. So, I just want to, and you can go back to these 2 papers, they explain very nicely. I am just repeating whatever is there in these references. So, you remember that we had this simulation cell, and we had this to be melt, and this to be a solid, and this to be a melt, and this was the z direction, and this is x or y direction, and so you will have this coming out as y. And what we do is that we bin along the z direction. Okay. So, and the binning can be done at 2 different levels. One is called coarse averaging. Okay. So, what do? We bin, we bin, and in every bin we look at every atom, and we have defined an order parameter. What was the order parameter? This was some summation over neighbors, and we summed the R I j that you actually have with the R I j for the ideal lattice for that shell. If it was a solid, at these ideal distances, the chances of seeing the another atom is high. So, you will get, so this is what we plotted as a function of this z direction. So, you found that lots of points were there, that was in the melt, and lots of points were there, that is in the solid, and you again go back. This is what we fitted to a profile which was a tan hyperbolic. Okay. Now, this averaging that you do, you can see that the data is very scattered, and to get a decent average out of it is the key, and we obtained that after doing this smoothing process. And smoothing is very usual nowadays in data analysis. So, if you go to one of the R tutorials, for example, on data analysis, there is one small book somebody has written and posted it for free in the R documentation section, which talks about, among other things, smoothing also. And there are many different ways of smoothing, and there is one particular finite impulse response FIR filter is what we use in this methodology. But smoothing itself is a generic technique. Like I said, anytime you connect your computer to any of the data acquisition systems, they all do smoothing, and sometimes they do not even tell. So, it is important for you to know what it actually is doing, and we give this exercise as a lab example. We take the raw data from our stress strain curve that you get from the machine, from the computer when you conduct the experiment, and you just take the raw data and give it to the students, and you do this experiment. The on screen you see the Young's modulus for example. But if you are given the raw data, it takes lots of effort to get the Young's modulus correctly. And the typical thing that is done there is smoothing by binning, which is something that lots of people got used to because of COVID, right. COVID data is also reported as average over the last 7 days, that is to avoid fluctuations. And these fluctuations, there are also systematic fluctuations that come about. I think in England for example, the data on Monday is always lower, which probably is a good thing to happen, you know, start the week with some good news, then it starts climbing up. That is because the data that got collected over the weekend did not enter the system. Okay. So, slowly it gets entered into the system and the average goes up, and then again over the weekend it drops. So, Mondays you will always find this methodical lowering of. So, this averaging process is a very simple one. So, you have a set of data points. So, what you do is that you take 4 or 5 data points and you put the average of them here, and take the next 4, put the average there, next 4 put the average there, next 4 put there, and then you can try to sort of fit and get the trend in this kind of very scattered data. So, this is one type of smoothing, that is sliding average it is called. Okay. So, you can take sliding average and you can smooth it. So, in this example what David Chuck recommends is to use a coarse average which is of the order of interplanar spacing, okay. That is coarse, okay, in these simulations. If you split the interplanar spacing into some 25 or 50 parts, that is called the fine average. Okay. Now, the coarse profile is extremely sensitive to your binning process. Okay. If you use different binning parameters, you will get different numbers. That is the interface. Suppose if I identify this as the point where the interface is, right. These are the two solid melt interfaces. Then if you use a coarse profile to identify this point will fluctuate. So, we need a process which is independent of how you did the coarse graining. Why should you do coarse graining? If you do not do coarse graining, you do not get, so every atom, you know, you have a Z this thing, if you do not take a slice of X and Y and get an average, then there are lots of fluctuations. I mean, you can go to every atomic site, you have some peak basically. And what we are interested in is to know whether it is solid or melt. So, in this case, to every site you go or every atom you go, the number of nearest neighbors will change. On the average, it will be if it is BCC 8 in the solid, and it will be less than 8 in the melt region. So, every point will have different. So, you want to average, and that is why you are binning and averaging. And so, you have to do it in such a way that these interplanar level fluctuations are smoothened out, but there is a overall structure that you see, which is that it is melt and this is solid and it is melt. The averaging should not be such that that information is lost, right. Where the transition is happening from melt to solid, we still want to capture it. So, to do that, the fine scale profile. So, you initially prepare the fine scale profile. How do you prepare the fine scale profile? By binning it at a much finer this thing than the interplanar spacing. And you can see why you need such fine average, right. Because you are near melting temperature, the atoms have their velocities. So, you can go to interplanar spacing, not all atoms align in the Z plane, for example, at the same point, they are slightly off here and there. Okay. So, you need to account for this fact, that is why you have to very finely average, and maybe in this small bin 1/50th of lattice parameters, several atoms will be there, then you will get their data, next one will have few more, next one will have few more, and at the end when you finish the process for one interplanar spacing, you will have as many atoms you would expect in one interplanar spacing in that plane. Okay. Now, that is the fine scale data which we are going to use this finite impulse response filter and coarsen it. The data then gets coarsened, Even then you get data points which are lying like that, but now it is easy. It clearly distinguishes the solid from the melt, and you can fit and you can identify the interface, and several things that I am going to show today depend on these fluctuations. We want to track them, we want to track them accurately so that we can get the properties of the interface from these fluctuations. So, what is this finite impulse response filter? So, Fn is a fine scale profile, then we filter the profile. The filtered profile is called Fn bar, that is obtained by going from minus n to plus n. So, there are basically 2 n plus 1 points over which you sum. Wk is the weighting factor, and we need to determine what it is, and Fn plus k. So, every point you take, you weight, and like I said, this kind of filtering is common. You will take one point, 5 point this thing binning, for example, smoothing average, for example. You will attribute to the third point the average from 1, 2, 3, 4, 5. For the fourth point, you will attribute 2 to 6. For the fifth point, you will attribute from 3 to 8, and so on. You will smoothen the data. So, local fluctuations will go away, but you are not taking large number of data points that you average out. For example, if you have a data, let us say you take 2 or 3 points, you will get this overall trend. If you take some 10 points here, you will probably get an overall trend like that, right. So, you need to choose properly so that you get the trend only by smoothing out local fluctuations, not the global trends. So, then it becomes important to know what is this n over which you should smooth. Okay. At this point, we do not know the weights, we do not know the numbers. So, filtering should be smooth to large oscillations in the fine profile, but it should not lose the trends. So, we choose the weights Wk by minimizing this quantity called S, and S is basically, this is a central difference. So, what does this central difference give? Fn plus 1 plus Fn minus 1 by 2 minus 2 Fn. This is central difference for what? There is a factor missing, but Mohan, you agree with him? It is second derivative, right? You do 2 times, and that is why it is also written helpfully as del squared. So, second derivative represents what? Curvature. Okay. So, basically you are minimizing this quantity, and you choose weights so that this quantity is minimized. There is one more step. So, David Chack and Laird show that you can take an n and you can try to do, if you do, finally you end up with a profile that is Gaussian, which is not surprising, because if your atoms are oscillating randomly and if you very finely bin, the probability of finding the atoms in different bins will go as Gaussian, you would expect, about the mean position. Okay. So, the averaging should be done using a Gaussian profile. This is also used as a blind technique for smoothing. Gaussian profile smoothing is very common. Okay. Many of the data analysis people use, but they will just use it as one more tool. Okay, I can try Gaussian profile, how does it look? You try to smoothen. But in this case, there is a physical reason why this profile works well. So, David Chack and Laird say that, okay, we tried everything, it turns out to be Gaussian. So, we will put the Gaussian in the first place by hand, so that things are easy. Yes.
But ideally, in the crystals we see almost we deviate from the Gaussian.
No, it is a classical particle. If you look at its velocities, it would still go as Gaussian. Okay. And whatever unharmonicity because of which it oscillates more on one has already resulted in the lattice parameter expansion. Then about the mean position, it is a good approximation, that is what Ferdi called as harmonic approximation. to assume that the atoms are, see, the unharmonicity already has led to the lattice expansion, right. At this temperature the lattice would have expanded. So, it is not going to, because it could not go too much on that side and it oscillated. So, now it has found a minimum about which it will oscillate, and you expect that you can assume that it is harmonic at this point and it will have this profile. Okay. So, that is the profile. So, we want to know how to choose this 2n plus 1, which is basically the question of choosing the n, and we want to make sure that we do not lose any information. So, we assume the shape of the filter to be Gaussian, that is W k is some A k. Now, I missed it. No, sorry, this is not Fourier. W k is the weight for the kth factor that is in the exponential, the k is there, A exponential minus k by epsilon whole squared. This is Gaussian profile, exponential minus mu x squared, and the k runs from minus n to plus n. So, there are 2n plus 1 of them. We want to choose the epsilon, right. We have transferred the problem of determining the W k to the problem of determining epsilon. Epsilon is basically the spread factor in the Gaussian, that is what we want to know. How much should I assume that it is spread? That minimizes yes. A is determined by the constraint summation W k should be equal to 1, because those are weighting factors. The 2n plus 1 of the W k's, if you add, it should add up to 1. So, A is easy, 1 by summation k minus n to plus n. I do not know why it did not go here, it should be here, exponential minus k by epsilon whole squared. Okay. So, we know A, we need to determine epsilon. Once we know epsilon, we can know all these terms, and then we can add them all up and get A, and we need to know how many of them we are going to sum. Okay. And all of that we are going to do by minimizing this S. That is basically the idea in this FIR filter. So, what we do is that we plot logarithm of S as a function of epsilon, and those curves look like that for one n. You do for another n, you do for one more n, so you choose this n and this epsilon and do the smoothing. David Chuck and Lade paper has everything, and this logarithm of S versus epsilon is something that we saw in the thesis. It is just a trick. You can see from this that you can keep on going, right. Maybe one more you go, it goes like that, right. So, do I go there for this n? We keep on going. Or do you expect it to go like this? You have an interplanar spacing and you have some number of atoms in this cross section, and you are already splitting it into 50. Let us say this plane had 10 by 10, and let us say some 4000 atoms, right. And you are trying to also do a smoothing, and you are trying to do calculation and so on. So, you take this spacing and you split it into 50. So, on the average you would find in each of these bins how many atoms? 4000 by 50. It is not really, I mean, it is concentrated in one part. You are really going to find very few atoms very far away from the mean position on either side. So, most of them would be concentrated closer to, but you would still find per bin on the average 4000 by 50 or 4000 by 100, right. 4000 by 100 is only 40 atoms. Okay. So, your statistics will become bad again if you do much finer gridding, and finally, you will reach a stage where there is in each grid maybe there is 1, maybe there is not even 1 and so on. So, that is not going to help. Okay. So, typically we have also found, and what people have found is that this number ranges somewhere between 25 to 50 for reasonable system sizes that we use. Okay. Maybe you have 10,000 or 100,000 in your one plane, maybe you will be able to go to 100 or 200, but that is not the scenario that we see. In the case of David Chacklade, they get this n as 25. Okay. We got what 40, 46, okay. Because our system size is large. So, you can do a little bit more of fine binning and get enough number of particles in each bin to get a good statistics. But for the system sizes we use this is sufficient. So, this is how we do the optimal choice for the FIR filter, for the order of the filter and the Gaussian profile parameter that we need to use to smoothen out the data. Okay. So, I think Sushil has Sushil, you have shared this MATLAB program which does this plotting or fitting, right, with me.
MATLAB program is for this thing, the order parameter one. So, one that I have shared you, that is for stress profile.
Yeah, this is the Gaussian filter dot m, right. Oh, this will not. Why would it not give me? Sorry. Okay, so, this is a MATLAB program which takes, and you can see D2F5 for example, GK plus 1 plus GK minus 1 minus 2 GK, and S is S plus this. So, this is the quantity, and you do it for different n and for different epsilon, make these plots, look at the plot and choose the curve for which you want. Then minima can be determined by just looking at the data or by other processes. Okay. So, this is a script which I will post for you. Some of you who start doing these simulations might find use for it, and it becomes essential for many things to have this kind of smoothing.
So, once you get n in epsilon value, after that in the script in the file only just change with this, fix the n in epsilon value whatever is there, just put that and use the stress data.
Okay. Any questions? Okay. There are no questions. I want to talk about another topic which is also very important, and this is the point where we start making contact with other models, specifically in the phase field solidification literature. The way to obtain the attachment and interface anisotropies, the attachment kinetics and interfacial free energy anisotropies is one of the ways that is typically used is to do a molecular dynamic simulation, get this information and put it into a phase field model. There is a nice paper by Ramakrishnan and Shankar Subramanian in ACTA, where they are looking at nickel aluminides, and they show how to evaluate these two parameters, the interfacial energy anisotropy and attachment kinetics anisotropy. They do not use the capillary fluctuation method for the attachment kinetic anisotropy, they use what is known as a free solidification method. You will see what it is once you know what the attachment kinetic anisotropy is, and then they take these values, put it into a phase field model to do solidification simulations using phase field model, and they discuss other things that happen in this system. So, I want to show you the formulation for these two, how to evaluate these anisotropies. These are two different kinds of anisotropies, as you can see. Interface is a energy, it is a thermodynamic quantity. The other one is a kinetic quantity, which is attachment. Both of them can be anisotropic, and typically you get, like I said, one would expect that okay, you are at very high temperature, then these anisotropies should not be important, and they are very small. Typically they are what, 3%, 4% kind of anisotropies, but they do have a large say in how the microstructure evolves, especially if it is dendritic solidification. The dendritic arms, for example, are aligned along specific directions. It is known experimentally, and so can you get that in a simulation? If you do not put these anisotropies, you will get what is known as a seaweed structure. It will grow in all directions equally, and you will see this, but that is not what you see experimentally, and so it becomes important to get this. And there is this person called Kenneth Librecht, who studies ice crystals, and in ice there are many interesting things that happen, where there is this competition between interface free energy anisotropy and attachment kinetics anisotropy also starts playing a role. And depending on the supersaturation at which you grow the ice crystals, you can be in a and the temperature, if you are close to 0, which is like the melting temperature for ice, then you have the attachment kinetic anisotropy primarily controlling the morphology. You get lots of dendrite kind of structures, and ice is hexagonal. So, you get the arms with hexagonal anisotropy. Then if you go to very low temperatures, I mean some -40 or something, then you will see everything to be faceted. That is because there the kinetic anisotropies are not dominant, it is almost growing at a quasi equilibrium kind of growth, and there it is the interfacial energy anisotropy that controls. Somewhere in between, so there are these atlases of temperature versus supersaturation, how the ice crystal morphology looks. Librecht's papers have some very nice ones. You will see that there is a competition between the two. You will see some faceting, you will also see some branching. Faceting is typically interfacial energy, branching is typically kinetic anisotropy, but you will see a transition regime over which you will see both facets and branching happening in the ice crystals, and they produce very nice morphologies. Of course, in real systems there is one more complication, like Freddie will say, but we do not see it here. As the ice crystal is falling, so it is starting at some point and it is reaching the ground. These snowflakes get these different shapes, and each is supposed to be unique. And Librecht also has a book where he has photographed many of these snowflakes, okay, a big book full of snowflake photographs. There the conditions of both temperature and the supersaturation change, so it is not a constant anymore. So, under those conditions what are the morphologies that come about is what becomes interesting, okay. And it is a very complicated problem, and there are many studies including some phase field ones. It is also a problem of practical interest, not in this kind of situation, but if you go to some place like Siachen, there are always avalanches that happen. And why do avalanches happen? So, ice starts falling, at that time the ground temperature would have been something, and now the outside temperature is going much below. So, you have a thermal gradient established from the ground to the top surface is at a lower temperature, the surface, near the earth's surface the ice is at a higher temperature. So, those molecules debond from the surface, go through the porous structure and deposit on the towards the outer side, where they grow these nice faceted 6-fold columns. Now, these columns are very brittle, on top of it the ice has debonded. So, any small stress can lead to this entire thing coming off the surface, which is what is called as an avalanche. So, sometime back Funny and me, we had a project with our snow and avalanche study establishment, where they were interested in knowing, and they do many interesting things, and you are supposed to hear some acoustic signals when these things happen, because these ice crystals break and you can follow the sound and then you will know, and you can track where it is happening. And of course, Snow and Avalanche Study Establishment also do other things, like when these avalanches happen, they should not affect the traffic flow for them. So, they build bridges and roads in such a way that even if avalanche happens, it will just pass through the road and fall on the valley, and it will not affect their traffic. So, in any case, so this is an important problem in solidification and in many systems where there is phase transformation that is happening, and the parameters for that can be obtained using typically molecular dynamic simulation. So, that is why the interest in evaluating these anisotropies. Again, there are two papers which I strongly recommend that you go through. Both are from Hoyt, Asta and Karma. One is from 2001, the second one is 2002. The first one talks about method for computing the anisotropy of the solid liquid interfacial free energy, which is a PRL paper. So, it is a very short paper, 3-4 pages, and I will summarize what they are doing. The second one is a slightly longish paper, atomistic simulation methods for computing the kinetic coefficient in solid liquid systems, because they discuss three methods. There is a forced solidification method, there is a free solidification method, and there is a fluctuation method. In fluctuation method, if you are already evaluating the anisotropy using the fluctuation method, this happens to be just a bonus thing that you can get. Do not have to do more work than what you do for the solid liquid interfacial free energy anisotropy that you calculate. But this paper also is written very nicely. You can just take a look at it and see what they do. Okay, why is interfacial energy anisotropic in solids? Like I said, the classic picture that we have in mind is that if you take a lattice, and now these are surfaces which are cleaved along the 1 0 0, but if I cleave along some random direction, then you will see that I break bonds. You have to count how many of them I have broken in a simple broken bond model, and you can show, as Porter and Easterling does, that the number of broken bonds per unit area on this surface goes as some cos theta, where theta is the angle that this plane makes with the x axis. So, cos theta you can plot, it has cusps. Okay. Now, when you have cusps, what does that mean? Any orientation other than that, if the system tries to take, the energy increases, right. You have this is a point. So, any plane which has that normal has the lower energy, slight deviation will increase the energy a lot, which means the system would prefer to take this, and there is a theorem called Wolff's theorem, which says that if you make this plot, what is this plot? You take a crystal, go from the center in that direction for that plane, what is the interfacial energy? So, which means any plane that makes this angle is higher interfacial energy, any plane that makes like 1 0 here for example could be one of these, then it has a lower energy. So, the inner envelope of this surface in 3D is the equilibrium shape. Yesterday Ferdi was showing in MC simulations, you can see it looks like they are all made up of 1 1 1 planes. Okay. So, that is the interfacial energy anisotropy. If you go to a textbook like Porter, it will also tell that because this argument is based on breaking bonds, this is true only at lower temperatures. As you go to higher and higher temperatures, where entropic effects are more important, you are supposed to get more isotropic interfacial energy, and that is also known as roughening, or it is some sort of roughening, where the interface no longer is remaining faceted, it becomes. Having said that, even though we are at the melting temperature, in many solids, at least metallic systems, this anisotropy is important. It is very small, 2%, 3%, but it would still have a say in how the morphology comes about. So, this is the origin of interfacial energy anisotropy. So, what is attachment kinetics anisotropy? In attachment kinetics anisotropy, again I want to take a solid and I want to make it come into contact with the melt. I can do that by, in this case it is the 100 interfaces which are in contact with the melt, but I can make that with 110, 111 and so on. Okay. Now, when you do that, the solid will grow if there is a driving force. What is the driving force? Undercooling is the driving force. So, delta T is the driving force, that is you are below Tm, the melt is below Tm. So, the solid will invade the melt. So, it will invade the melt with a velocity. The mu coefficient, the attachment kinetics, is basically the proportionality constant. For a given undercooling, what is the velocity you achieve? That is what mu is, and that is different if you make different planes of the crystal come into contact with the melt. We want to know how different it is. Okay. That is the attachment kinetics anisotropy. Again, in a phase field model, this goes as a parameter into the model. So, you have to put the right parameter if you want to simulate the microstructure better quantitatively. Okay. Okay. So, capillary fluctuation method is a method which assumes that the solid and melt are at equilibrium, and you need to have a way of distinguishing the solid from melt. So, you need to have an order parameter, and the typical order parameter that we use is by looking at the nearest neighbors and distinguishing solid from the melt, and that calculation always involves also smoothing. Without that you cannot get reliable numbers, there will be lots of scatter and you will not find any useful information. That is why we have talked about how to define this order parameter and how to smoothen it and get a proper profile. Hence, you will be able to identify where the interface is. Once you know where the interface is, then fluctuations in the position of the interface can be related to a quantity which is known as interface stiffness. Gamma is the interfacial energy per unit area. Gamma prime double prime is nothing but where theta is the angle that represents the orientation. Okay. Why is it called interface stiffness? You can see that this del squared gamma by del theta squared, if it is very high, the interface is very stiff. The interfacial energy increases large for small changes in theta. So, the interface would like to keep the theta. If the interface keeps that orientation, you get a faceted interface. If this quantity is small, the interface is not that stiff, which means it will explore all orientations around this orientation, right. So, that is why this quantity is called interface stiffness, gamma plus gamma double prime. It basically tells what are the kind of fluctuations you can expect. So, by looking at the fluctuation, then you can estimate what is this gamma double prime is, which basically tells you what is the how the interfacial energy is changing with orientation. Okay. So, there is one trick that is shown in this paper by Hoyt, Asta and Karma, which is to say that it is preferable to take a thin slab to do your simulations. What do we mean by thin slab? So, we take a long one and it has a breadth and it has a width. Like, so it is a ribbon. So, it is long in one direction, it has a breadth and width is larger than the breadth. Yeah. Okay. B is far less than W. So, it is basically a ribbon. It is taken in that fashion because we define the h of x as the height of the fluctuating solid melt interface. So, you have solid, you have melt, and so So, the interface between them is fluctuating. The paper has a much better picture. Okay. So, this is melt, this is solid, and the solid melt interface is always fluctuating. It does not remain flat like this. Okay. And what we are doing, this triangular bracket, as you know, is an average, large number of simulations. So, we measure the h of x, because this is x. The h of x is basically the y, where the interface is at various x points, and that is fluctuating. Okay. So, that fluctuation in 3D, if you take a square interface, apparently goes as log of w, whereas if you choose this kind of very thin geometry, it goes as w itself. So, you can get much better statistics if you choose this geometry. So, the only thing you have to do is to do a MD simulation where you have a long one, like we had for the solid melt interface this thing, but we had a square cross section, but you reduce the cross section on one of the directions. Okay. So, you have now a ribbon which is undergoing fluctuations, and you track the fluctuations, and from the fluctuation get the interfacial stiffness or the anisotropy in the interfacial free energy. So, once you have this kind of fluctuation, it is obvious that it can be split into Fourier transforms, right. Any random profile can be written as a sum of Fourier series. You can think of Fourier transform in the infinite dimensional case as, if you have anything in this room, for example, I just need a basis which has 3 units, right, directions, right, x, y, z. In 3 dimension I can represent. If you have an infinite dimensional space and you want to have something equivalent to ijk, what is the property of ijk? If I give the I component, the j and k components can be independently determined, right, it does not affect. So, there is a sort of orthogonality, they do not talk to each other, they are independent, right. So, if you want to have similar representation for an infinite dimensional space, functions are living in infinite dimensional spaces. So, you want to have a representation in terms of basis vectors which are orthogonal to each other. Of course, you can normalize. So, you can have an orthonormal basis set for an infinite dimensional object, that will be your Fourier transform. You can take any random thing and you can write it in terms of so much of cos 1 x, cos 2 x, cos 3 x, sin 1 x, sin 2 x, sin 3 x, and so on. So, that is what it is. Okay. So, we split this fluctuation that we have in the Fourier space as to be made up of these components which do not, cos kx, cos Lx, if you have integral k equal to L, it will give you some value, any k not equal to L, it will give you 0. Sin kx, sin Lx also will give you, except when k equal to L, and any cross term cos kx, sin kx will all be 0, because one is odd, the other one is even. So, you integrate, you will get 0. So, it has this nice property, and you can think of Fourier transform as this way of writing the components in a infinite dimensional system. Okay. So, by the way, there is a book on partial differential equations by Arnold Sommerfeld, which is a nice book. Within the first 5 pages or so, he motivates Fourier transforms, and the way he motivates Fourier transforms is slightly different. It is by saying that, suppose you have a set of data and you want to fit, suppose you make a least square fit. If you did a first order fit mx plus c, now you realize that no, this is not good enough, I want to do second order fit. You have to evaluate all the 3 components again, right. You can't say, okay, the linear term I already had, I will use that a, I had a intercept, I will use that b, now I will only evaluate. If you demand that you should have this property, that arbitrarily you will do to whatever extent you want, and when you want to extend, it should be independent of all the previous ones, whatever you have determined should be okay. If your definition of error is L2 norm, then Fourier transform is the basis that you get. And all these special functions that you get, you know, some of you might have solved the hydrogen atom or something, there are many special functions. Each one of them is a basis set that you get if you define your error in one way. I think logger is if you define the modulus to be minimized, right. You can minimize the error, but by taking the modulus. If you do, I think the basis set that you get is logger polynomials, something like that. So, in the first few pages he explains this, and that is how he motivates Fourier series and then the Fourier transform from there by going to a continuum limit.
Yep. Views of your coordinates. So where is the solid liquid interface in this upper sketch, this long bar?
Okay. So, you need to put the solid also below. So okay, let me redraw this. Half of it is solid, half of it is melt.
So in this direction.
Yeah, in the y direction is how they typically take, but that is just a convention, you
Because
don't have to.
wrote that you have infinite y-axis.
Yeah, okay. So I think I switched the sorry. Yeah. So this is y, and so you have the melt, and so this is y. So this is the direction in which you should have the ribbon. So this should be x and this should be z. Sorry. Okay.
So the height of the fluctuation is h of z.
Yeah. So h of x, because x is the wider one, and I am assuming that this in this direction this is larger than this. So the plane is this plane. And this direction is along x, and I am assuming that this thickness is much smaller than this x.
Okay.
This is w and this is b, and b is far less than w. Okay. So you basically have a molten thing, not too much, spread on a ribbon.
But the melt is a thin layer on top of a thin solid.
Thin solid, yeah.
And then it's
In the so that fluctuations can set in, and you can. Okay. Okay. So let us assume that the mean energy in each Fourier mode is Ek, right. K basically is 2 pi by lambda. So for each wavelength, but it can go as cos and sine. So there are 2 degrees of freedom, and so it should be equal to 2 times half kBt. So kBt is basically equal to Ek. Okay, that is equipartition. And you can use this definition to evaluate gamma, which is nothing but the integral of gamma as a function of theta over ds. Remember, we have this kind of fluctuating interface. So there is some differential geometry which says that the arc length, how is it related to dh by dx, and what is theta. These are very common, and you will see some differential calculus textbooks. The famous one is Thomas or something.
I think it's similar for dislocations where you
Yeah.
the line tension.
Yeah. And in the phase field, when they do the asymptotic analysis, it is the same. So in all of this, you somehow do this geometry of taking it, and it's an approximation. That is why you see in both cases it is written as an approximation. So very close, slightly deviating from the flat surface, you can do this. And then if you do and evaluate this interfacial energy, you can correlate this Ak squared. What is Ak squared? Amplitude for the kth component. You take that square and you average, and that is linearly related to the interface stiffness. More specifically, this average of AK squared is KB, which is known to us, Tm, that is where you are equilibrating, known to us, B and W are simulation parameters known to us, K squared, that is what you will plot, A K squared for each K squared. So, you can see that all these are constant. So, then you make a linear fit, that slope will give you, if you plot 1 by A K squared versus K squared, the slope will basically give you interface stiffness, because that is proportional to this and the other quantities are known. Okay. So, why is this gamma double prime is in the denominator? Because that is the energy cost associated with local bending of the interface. If it is very high, the interface will not bend. If it is low, the interface will keep fluctuating. So, basically we are getting the information about how stiff is this interface from this. Hoyt-Asta-Karma paper is good. It refers to some of the earlier papers which started the capillary wave, and strangely I found that that theory itself also came because of some simulations that somebody ran, and they said that it is not matching. They did an Ising model and they said that capillary fluctuation theory results are not matching with Ising results, and then they point out that Ising model has anisotropy for the simulations that was done. So, you need to correct, and this is a correction term, and this was done long back. So, now afterwards in 2000 they decided to exploit this by evaluating anisotropy in the MD simulations. So,
the other side, that's another example for the fluctuation dissipation theorem. Yeah, I mean, you can determine, say, elastic modulus specific.
Oh yeah, yeah.
From the fluctuation of the corresponding quantity. Yeah.
Yeah, you have already talked about these fluctuations. Yeah, so this is one more example along same lines, right?
I mean, here you have your interface corrugation, which is also this factor K2T is characteristic in which
Yeah.
is 1 over the stiffness. Except that here it's made for different K vectors as well.
Yeah, for each mode you are doing, and so basically we take this, so make the curve, and there is a linear regime where you fit for this. So, okay, this is clear. So, Sushil, is it clear? You can implement. So, now kinetic coefficient mu is the proportionality constant between interface velocity and undercooling, and there are 3 methods of evaluation. One is called forced solidification, other one is called free solidification, the third one is the fluctuation method. In the forced and free solidification, as the terminology says, you impose an undercooling, or you take a system with a given undercooling and then start the simulation, measure the interface velocity. Of course, if you do it for different planes in contact with the melt, you will get the anisotropy directly. So, basically we are trying to find out for a given driving force, what is the velocity, V equal to mf, m is the mobility. So, interface mobility is what we are calculating. That is called kinetic coefficient, because there is this process of atom jumping from the liquid to the solid and becoming part of the solid. Okay. In the fluctuation method, this is also explained in the Hoyt-Asta-Karma paper very nicely. Suppose delta ns is the change in number of solid atoms from the average, and that decays, the correlation of this change in number of solid atoms decays as exponential minus t by tau, where tau is the relaxation time, which is related to the thermodynamic restoring force and hence related to the mu. So, you can just take the averages of AK. Okay. I am not writing the expression, it is there in the paper, and you anyway calculate AK for calculating the interface energy anisotropy. So, one more correlation you generate from the AKs at different times, using that you can get the kinetic coefficient. Okay, so that is also very simple. I mean, again goes back to the same fluctuation. So these factors of kBt etc. will enter into your equation, but it is rather straightforward to use the same Fourier mode amplitudes that you have calculated to evaluate the kinetic anisotropy also. So, because of which I think it is a nice method that you can get both anisotropies at the same time. Even though, for example, Shankara's paper they use the free solidification method, they do not use this fluctuation method. I do not know why, even though they use the fluctuation method to evaluate the interface anisotropy and show that in this nickel based superalloy it is of the order of 3 to 4%. Okay, so I think I have come to the end of this part. You have any questions or clarifications? Yeah.
The equation, so it's a fluid little if you keep alive the temperature, how do you choose the relations? Normally we have the liquids, it's our range, right?
Yeah, but you will do the simulation for a given composition, right?
Yes.
The MD simulation will be done for a given composition. So, you will have that temperature at which they are at equilibrium and you will evaluate, right. What is the
Okay, I mean at a given temperature, okay.
Right, kBTM is there, Tm is that temperature at which you are doing the simulations. So, irrespective of, so if composition wise in fact, if you change the interface itself, that temperature will change. Like I showed in the case of iron, the melting temperature or the equilibrium temperature at which solid and liquid are in equilibrium changes by a few degrees if you change from 100 to 110 to 111. So, it is not a same value even for the same crystal with the given composition. If composition changes, that will also change, that is all. Freddie, you had.
Averaging over K in the last slide, does it mean that it treats also, I mean, very fine fluctuations should be less favorable than coarse fluctuations?
Okay, let me go back.
I think the last slide.
This one?
Yes,
This one, okay.
So it takes the average over the amplitudes of K.
Node case, yeah. And that is related to the delta ns. The fluctuation is basically the.
But if you take all fluctuation, all modes, this means also that you have extremely fine fluctuations.
Okay. So
isn't it?
Okay, so the linear regime where we fit is for small k, which means it is large lambda. Yeah, I am assuming that this averages will also be done for those modes.
Okay.
Yeah. I don't know if I have the paper.
I mean, it's a bit like in Spinoza decomposition that you
Yeah, the linear. Yeah.
Short wavelengths.
Yeah. I do not see too many variations, but they do give the linear regime where you have to do.
What does it mean? Is the melting point the crystal differs on the?
Yeah, okay. I mean, I probably shouldn't say melting point. What differs is the temperature at which the solid and melt are at equilibrium.
Yeah.
That depends on which facet of the crystal you are exposing to the melt, because of which our simulations are done at that temperature. So, all these evaluations, when we say kBt, the T should be that temperature, and if you equilibrated with 100, let us say that for iron happens to be 1820, but for 111, let us say that is 1822, then the T that you will use is 1820 or 1822. I mean,
Yeah, but what happens to a crystal, I mean a small nanocrystal, if you immerse it in a melt, which is between the 110,
So,
the 111 and the 100.
yeah, I would expect that it will quickly reach its equilibrium shape, which is to the on the side where it is not favorable, atoms will become part of the melt. On the other side where it is favorable, it should so it should get faceted according to the interfacial energy.
Yeah, but still there would be a gain in free energy if you dissolve this facet with a lower melting point.
I dissolve the one with lower melting.
I mean,
Oh.
assume you have a rectangular crystal.
Mm-hmm,
You have a low melting point here and a high melting point here.
mm-hmm.
So
But you are keeping the melt at some temperature.
you put the melting melt temperature in between these two melting points.
Okay.
So then this facet would migrate in this direction because it dissolves.
Mm-hmm.
But this one would migrate in this direction. So what's the stable point? There must be a stable point.
And in the process, the melt temperature will also change. And finally, whatever melt temperature at which you equilibrate, and in general we find that it is always the favorable interface is 100, means it will for the given configuration still have the lower energy under that constraint, right. I mean, we are saying basically that the fraction will change, my temperature will change, and
should change to 0, shouldn't it?
it should change to 0, because that is when equilibrium will be achieved. In general, what happens is that the temperature of the melt will also rise or cool down depending on melting and this thing, and it will reach the equilibrium.
If you work at constant temperature, this should not change.
If you work at constant temperature,
I mean, I
then
think
the
I mean, you have this problem in surface physics that the work function also depends. So it's basically the energy to
remove an electron.
remove an electron from a crystal or so. That also depends on the orientation of the surface. I mean, there it's perhaps even more obvious. So it's not well defined, so to say, because then you remove an electron here, you place it here, and then you would have a constant current or so. Yeah? So the surface physics people, they always keep this question about.
So, in our simulations, what we have found out is that if you are not careful about this temperature, let us say for example, it is 1820 or whatever, and then you are okay 1821, maybe it will move the interface a little bit, but if you have very high or low, that is what the potential energy curve is, it will either solidify or melt completely. But we have not immersed a crystal completely inside and see what happens. I would still expect that it would melt. No, his question is now, where does it reach equilibrium? Does it just take off and run away, or there is a way it can reach an equilibrium, right, Ferdy?
Yeah.
Yeah. So,
that's how we are talking the balance, right? So balance between both load planes. So one which is favored keep on growing.
should grow, right?
Yeah. And one which is not favored, it will arrest there and.
Yeah, but then is this higher melting point part just vanishes, then the material dissolves.
Yeah. So,
But might be higher melting point we are talking, but that difference may not be the same.
yeah.
Because just we are looking at the rectangular.
So, in the step kinetics that does happen, right, that I know, that the faster moving one will go, so you will be left with, yeah, there is a.
So you have a crystal like this, here on this facet you have T melting point 1, and here you have a melting point 2. And you put everything in the melt
Yeah.
just in the middle.
Yeah. So, Freddy, what I think happens is that in cubic this will not be. So, it is always
Yeah,
warm.
it's
So,
just one
yeah,
element,
you will
it's
be
a-
able
yeah,
to
sure.
enclose the volume
Yeah, but
by the facets made by these alone.
Yeah, sure. But I mean,
Ha.
take this example.
Right,
I mean,
right.
Then
Because here you
Lower
cannot
melting
have
point.
that interface without having this interface. That is why we are running into difficulty.
the melting point here is lower.
Probably I think it may take the lens shape if this is the case.
But lens has a curvature, too costly from the interface energy anisotropy.
So you want to say it's changing its overall shape?
Yeah, morphology will change. I think in cubic, for example, you can enclose the volume by having all 111 and completely get rid of 110 or 100. So here we are having difficulty because we cannot think of having this crystal if those two planes go away, but I think in real case that is not so. Crystallographically, if that is of some energy, this will also be of the same energy. So you will always enclose this in a cube.
You take a tetragonal system.
Right. So in tetragonal, let us say the C is not favored, right? Then it should become a needle. Become a needle of.
Needle of zero thickness.
Yes. Yes, I see that. But there should be a point at which the radius where yeah, so I am just trying to see that the amplitude whether there is any. So this is the correlation AKT minus AK0 whole squared, if you take the average, that is related to the tau, which is the relaxation factor, which tells tau is related to mu through this constant. Okay, so this is the anisotropy evaluation, which generally is of interest to people who are doing phase field modeling. Okay. This is one of the ways to generate these quantities. I mean, molecular simulation people not often do this, but
they compare the different methods?
yes, Karma, Hoyt, Asta for the kinetic coefficient. Yes, they do. And there seems to be some theory from Gilmer and somebody else. What is that theory? So they even compare with that. Broughton, Gilmer and Jackson. So they have some crystalline growth kinetics theory. So all these methods, forced velocity, free velocity and fluctuation, and they are all compared also with this theory to say how well they perform and so on. Yeah.
The length along the interface.
Mm.
So we are keeping as thin slab, right? So how about this bulk equilibration on that?
Repeat what?
We are taking a thin slab.
Yeah. So you have a long one, and then you have a thick, and then very thin.
Interface, it is limited. That's what.
I think that is what helps. I mean, when they say that the amplitudes go as ln W or W, what they mean is that if you have you can also imagine, if you have very large one, the fluctuations will be limited, but thin one can undergo large amplitude fluctuation. So it is easy for you to follow. So this geometry is preferred. It's not like you cannot do, but you might need larger simulation, longer times, better averaging and so on to actually evaluate.
So the fluctuation, whatever we have, should not, beyond the bulk rate. So that should be taken care anyway.
There is a way. So you can now go to the I mean, the fluctuation is only where the location of the interface is. So bulk does not enter, but whether that interface will fluctuate more or less depends on how much more of the liquid you have above or molten region you have above. Okay. So you take a solid, you spread this fluid very thin, you see the interface fluctuates more. So.
Why is it so? I thought that the fluctuation length should be independent of the surrounding thickness.
No, they say that it goes as they had a reference 12 or something. I did not go through what that reference was. So they say that the mean square height of interface scales proportional to the width in this thin strip case, and it goes as logarithm of the width when you have a 3D system with a square containing a 2D square interface. What I am assuming is that if you have a square interface, the kind of waves that you can set in is different from when you have a strip. So, maybe it is easier to set up. The reference was I did not see what it was. 12 also is some karma.
I mean,
So.
if you have solid here and liquid here,
Huh.
the interface fluctuates.
So, but the interface now, the solid liquid interface is a square. What modes it will fluctuate is different if you make that a thin strip.
Oh, it's not the thickness of the liquid layer, but
The shape of the solid liquid interface, because you are not now taking a rectangle where one dimension is much smaller than the other dimensions. Okay. So, let me then talk about the last topic. Unfortunately, I do not have the microstructure results, which I tried to locate, but I could not, must be there somewhere, I did not see. But anyway, I will just talk about this and then we will close for today, and afternoon Ferdi has something to say, and we are winding up. So, mostly. So, we will see how, if we can complete things by tomorrow morning. And
So, your place repeat.
huh,
I think the mail should have sent me one of the folder like microstructure.
is there? Okay, very good. Then I have the full 35 minutes to talk about. This MDMC, no? Okay. Okay, I'll come back to that. That's okay. The images are sufficient for me to. I'm trying to do like Ferdi does, but yours is much more integrated. I have a separate tablet to Bluetooth. Bluetooth. So it talks to via Bluetooth, and so I can do the. Okay. So, till now we have been seeing that you can do MD, and for that you use lamps. You can do MC, for that you use sparks. Now, it is possible to do some Monte Carlo even using lamps. Okay. Now, that gives you several advantages, and several interesting problems also can be solved once you have this, and that is what I want to talk about. So, we want to do Monte Carlo and molecular dynamics using lamps itself. The kind of lamps fixes to do MC are limited. There are only 3 I found. I'll tell what they are. So, one is to swap atoms, which you know. So, it is obviously not kinetic, only for equilibration it is good. Which is not bad, because sometimes all we want to do is annealing, like the problem that we have in mind, we just want to do some annealing or equivalent of annealing in the simulation. The other one is grand canonical Monte Carlo, which you can have a GC move, which you saw is again useful for generating phase diagrams and stuff. Okay. There is some time stamped force bias MC apparently. I do not know what it is, and they gave some reference where this is described, which also you can do, but I am assuming that this is something to do with reactions or chemical stuff. Okay. You can look it up, at least whatever keywords did not make sense to me, but you can do this time stamped force bias. They call it as TFMC, that is what the fix is. Okay. There are example scripts for both MC for Monte Carlo in the lamps example directory. Okay. So, I had that. So, you will see two examples, one is called MC and it has in the context of some, for example, this is Grand Canonical Monte Carlo using LJ, and they say that this is comparable to some Frankel-Schmidt GCMC case study, figure 5.8, equivalent of that you can get using. And scripts are like usual, very simple. So, you can define, I am assuming mu is the chemical potential. So, you can do. So, this example file is there, and there is also another one, MC loop it is called. Yeah. This example file also is there, and we can even run, I think I ran it once. Yeah. This directory has input script that illustrates how to use LAMPS as an energy evaluation engine in a Monte Carlo relaxation loop. This is what in the list of lectures you see that I say that you use molecular statics. So, basically you have MC that is running, and the interaction you need, there are many different ways, and one of the ways, okay, you can assume on lattice. So, you have bond energies that you give. You can also assume, you do not have to assume lattice, maybe it is moving a little bit from the lattice position, you can use the MD which evaluates this using some EAM potential, for example, or LJ you saw. Use these potentials, you evaluate, and then you can use that to have your Monte Carlo move. So, these are available already. Okay. Please check it out, it is fairly easy to run, and I do not remember if I actually ran once and showed you results or not, but so this is what the MC loop does, but what we are interested is in processes like this. The problem that we were interested is that suppose if you take a system like copper aluminum and deform, and it produces lots of stacking faults, because with aluminum addition we know, we have seen that example, that stacking fault energy goes down. So, when you deform you will see more of twin boundaries and stacking faults. It is also known in these systems that aluminum atoms prefer to go sit at the stacking fault. If you just take this system and randomly distribute aluminum atoms and do a deformation experiment, which we have done, we published it also, and we are writing one more where there is a stacking fault and this system is loaded at different aluminum concentrations, it shows some kind of deformation behavior. But that is not really the correct deformation behavior that we are interested in, because if you have a stacking fault like that, if you put, let us say, some 4% aluminum, it is not necessary that 4% of aluminum will stay in the matrix, maybe some amount of it will segregate to the stacking fault. Now, once it segregates because it minimizes its energy. Once it does that, this binding energy then will make it harder for dislocations to cut through the stacking fault, for example, it can happen, right. So, which means the right behavior that is of interest to us is to do a study where I throw randomly, let us say 5% aluminum, but for the stacking faults that I have or twin boundaries that I have, the system should equilibrate. After that I should do my MD. The equilibration does not happen in MD itself. If you try to just load, MD will give you a behavior, but that does not include this diffusional time scale where the aluminum atom should hop and find the stacking fault and sit there and start changing things. That does not happen. Okay. So, we were interested in doing this, and for that Sushil has used this combination of MD, MC. First you throw, you do a deformation test, take the same configuration, do an MC, then do the deformation experiment, the results are slightly different. And the difference comes because, like I showed you in the other case, it is nucleation limited plasticity. Wherever aluminum atoms are sitting can act as a nucleation centers, and you saw with increasing alumina how much of that contribution was there for the heterogeneous nucleation, apart from the stacking fault energy coming down. Now, when the segregation happens, the stacking fault energy comes down, I mean overall contribution because of this binding energy is still comes down. So, the stacking fault is much more stable than what you would expect from the just stacking fault energy in that composition alloy. But the nucleation itself becomes harder, right, in spite of this largely or broadly the stacking fault contribution coming down. So, homogeneous nucleation has to happen, and homogeneous nucleation has to happen in a matrix which has very less aluminum. So, overall it is still like having pure copper. So, you see that if you do an MC and repeat the deformation experiment, the yield stresses, I showed you softening with aluminum, it was going down. It starts again inching back to the pure copper case. And we also are able to correlate. So, you can look at the number of aluminum atoms in different layers, and wherever the stacking fault is, you see the segregation or the enhancement of aluminum atoms. I think that is the figure Sushil said is available in this directory. What is happening? Right, Sushil? This is the one? Yeah. So, these are the regions where you have stacking fault. These are JPGs, so I can't write on them. So, it is the 6 aluminum percent system where the overall number of aluminum atoms in each bin, different layers you see, and you can clearly identify the regions where you have the stacking fault, where instead of about 50 on average it is touching 100. Okay. So, this kind of segregation behavior, it is known as Suzuki effect. I mean the geometry that we are looking at is this. So, you throw aluminum atoms in this green region, and then they will go sit here, and if you just randomly distribute and do a deformation behavior, and with this if you do a deformation behavior, you will see a difference before Monte Carlo and after Monte Carlo. If you look at the stress strain curve, there is a difference, and this difference is basically attributable to this segregation. This is how the profile was before you did MC, and MC did this. So, these kind of things you can do fairly easily using the LAMPS script. Sushil has also done another problem where this kind of thing is becomes important, because one of our other PhD students, Sandhya, has done some experiments on copper and copper aluminum. And if you do a deformation experiment and after some percent of strain you stop the experiment, you unload and you start loading it again. So, you expect that you will have elastic recovery and then you will go back and continue, which happens if there is no time delay between unloading and again reloading. It is generally said that copper does not have too much recovery and things like that. So, one would expect that okay, if I have some copper 1% deformed, brought it down to room temperature and again kept it, let us say 1 hour or 2 hours, and then load, if there is not much change to the dislocations, then it should follow the same curve. But in this case, after delay, it actually goes to still higher stresses before dropping and stabilizing to some value. And this dropping and stabilizing, it stabilizes to a higher value than what it would have done if it continued in the same experiment. So, this excess is typically attributed to impurities which go to the dislocations because you have some time, and then they start changing the deformation behavior. And the stabilization at higher value means that some of these never recover. You load, maybe some dislocations get detached and then start moving, but some are still there. with these impurities, that is why you stabilize to a higher value, because you have found a more favorable configuration for this dislocation network structure, at least some part of it which stay in the system. So, can we test this using a simulation? Yes, you can, and those are still under study. We have started the simulation, we have some results that look promising. So, I am not presenting them, but I am telling you the kind of problems where you can think of using these kind of combinations, or these kind of combinations becomes important for us to do. Okay. Yeah.
Why are you doing fast loading without MC?
Because that is what we did in Kamlakshi's thesis. We said, okay, we want to study the effect of aluminum, and we just threw some percentage of aluminum and started doing the simulations. First simulation was okay, because there were no defects, where we were only interested in the dislocation nucleation limited plasticity regime. But we also did another set of simulations, which is one of our thesis chapters, where we wanted to know how the dislocations interact with a pre-existing annealing twin, where also we said, okay, 6%, I put aluminum 6%, I do an experiment. So, you see some behavior, but we realized that that might not be what is happening in a real experiment, because in a real experiment, if you have an annealing twin, if you had some percent of aluminum, probably the twin has also collected lots of aluminum atoms. So, if you want to actually simulate the scenario where you have 6% aluminum in an overall alloy, but with some annealing twins, then that can be done only if you do an MC first, allow the structure to equilibrate configurationally in terms of aluminum atoms where they should sit, then do a simulation.
So, then it's a faster you just creating the cell and then I just do MCR.
Yeah. So, that is the right procedure. We are just somebody can ask, okay, how do you know that this happens? We are showing that if you do not do, there is a difference in mechanical behavior. Okay. And we are now able to correlate why that mechanical behavior is there, because the matrix now looks, after it removes the aluminum atoms, much closer to pure copper matrix rather than a copper 6 atomic percent aluminum matrix, or maybe it is a copper 3 atomic percent aluminum matrix with some lots of. So, how much of aluminum you add and how much of them go to these boundaries. So, that is why he is also evaluating the difference in interfacial energy with and without segregation, which at some level tells about the interaction of the aluminum atoms with the stacking fault itself, and sometimes he is finding negative values or something. So,
dislocation before the
no, the dislocations only nucleate during the deformation. That is why it goes to, yeah.
put the stacking fault.
We put a stacking fault. I mean, we actually put a twin boundary, which is like two stacking faults separated. We call them as annealing twins to mimic that a system with an annealing twin, what happens with the. So, we do form lots of deformation twins, and they also interact with the annealing twin, and sometimes they shift the annealing twin, or they de-twin this annealing twin, or increase the thickness of annealing twin. The strange thing that we found is that a dislocation approaches the twin boundary and then starts going back. Many a times it comes, gets stopped, it cuts through, or it nucleates another dislocation and so on. I think this is because the local dislocation structure is also important, but we are not able to find the evidence yet. Kamlakshi is still doing the analysis. What I thought was that you have a twin boundary, this dislocation comes, maybe it would have stopped, but maybe there is another dislocation either from the side or from this thing that is coming. So, the stress state locally changes and this dislocation realizes only after reaching there. So, it starts receding back, I think, but we still have not found. So, things like that happen if you have a pre-existing boundary. So, okay. Any other questions? So, I think I explained Suzuki effect and why MDMC simulations are done. So, I think I am done. That much.
I just wanted to show briefly one further example of this combination of, oh, I should switch on the screen here. Combination of Monte Carlo and molecular dynamics, very brute force method to combine these two. What's the problem here? Oh, okay. Why doesn't it? Okay. So this is, I can skip here. By the way, there's one package which is claimed to be also available, VCSGC, but I did not manage to get it running. So what I wanted to show is this one here by my student Tobi Stegmüller. He wrote just a wrapper in Python around the lumps procedure. Yeah? So he does the Monte Carlo step in his wrapper and then starts molecular dynamics again, just step by step. I said that's not very elaborate, but the advantage is that you can implement much more possibilities, in particular this residence time algorithm. Yeah? And just wanted to show here the result. The question in our case, we are always on the other side of the aluminum copper phase diagram, on the aluminum side. And as you already heard a couple of times, in aluminum copper, with small amounts of copper, you form these Guinea-Preston zones. And what is experimentally found, this is taking place at room temperature. Yeah, that's what we call natural aging. And what we found, what other people found, is that after a few days, this room temperature aging more or less stops. The question is, what is the reason for this? So here you see the technical details here at 300 Kelvin. There's one vacancy. And here you see the formation of the GP zones. But the interesting part is this one. So he put one GP zone into the crystal and let then the vacancy move. And perhaps I go back and forth. So here you see it's moving freely. But after a while, it enters this GP zone and then it's trapped there. So this vacancy is no longer available for further growth of these GP zones. And as this whole process is only working because you have an excess of vacancies, after a while, most of the vacancies are trapped inside these GP zones, and the process more or less stops. So what you found experimentally is, I mean, at these low temperatures, you would expect, if you look at the phase diagram or so, that nearly all the copper goes into GP zones. I mean, the solubility at 300 K is extremely low. But what is experimentally found is that only maybe 20% of the copper atoms go into GP zones and the rest stays in solid solution. Just counted in electron microscope, the number of GP zones and so on. And this explanation was given here. What he did is he used again this neural network potential, which I already introduced some time ago. This is a pretty high copper concentration, but this does not matter.
But that means that in these systems, the vacancy concentration should be slightly higher than equilibrium.
Yes.
All these excess vacancies are now stuck with the
right.
GP zones.
Right, yeah.
So the excess vacancies never completely go away.
That's what we suspect, yeah. And we did another experiment. A real experiment, not a computer simulation. We measured the dissolution of these GP zones. So they dissolve typically at 150 or so. If you do it at different heating speeds, heating rates, you see a shift. I mean, you can do it in calorimetry. You see the dissolution as an, endothermic peak. Yeah, and you see a shift of this dissolution peak for higher heating rates. Yeah? And then there are all these types of what is it called? It's not just an Arrhenius plot, but is it Kissinger plot? Or I forgot, some strange kind of plot from which you can derive the activation energy for this process, for the dissolution. And it turned out that the activation energy, if you believe our results, that the activation energy for this dissolution is not the activation energy for copper diffusion in aluminum, but far lower, about half. And if you remember, the activation energy consists of two terms, the vacancy formation energy and the vacancy migration energy, which are of equal order of magnitude. So if this activation energy is only about 1/2, I think it was 0.7 eV or so, this means there are pre-existing vacancies, yeah, which do the dissolution. You just have to get them away from the precipitate here. So this is another indication. I think this was all, and perhaps I think I have it somewhere here on the computer. I asked Toby to send me his script.
This using lamps as a library should also be in principle
right,
equal
yeah.
to this, right? So
where did I put it? Do I have it here? Ah, okay. So this one. No, that's not the one. I know that that I have it somewhere here, this Python script, but I don't know where I put it. Oh, here it is.
create system.python.
So it's a mess of Python scripts. I think the important one is probably this one here. So there was another complication. If in lumps you define a region like this GP zone, it for whatever reason cannot handle periodic boundary conditions. So if this Guinea-Preston zone extends over the box boundaries, you have two precipitates. So he also tried to handle this. And here is basically all kinds of operating system calls where he copies back and forth and creates an input file for lumps. And then somewhere here he does lumps run on two processors apparently only, which are the real lumps procedure here. So that's something one can do. I suppose there are much better ways to do it. But I think not all possibilities we have or we have discussed here for Monte Carlo are available in lumps. I think they don't offer this residence time algorithm. So if anyone is interested how this one was done, I could also upload this set of Python scripts here. So this was a short extension to this combination of lumps and Monte Carlo. I think there's much more in future because, as we heard, molecular dynamics is very limited in system size and time, in particular in time, while Monte Carlo can cover much larger times, and this combination for many applications will be quite powerful, and the better you do it, the better results you will get. Okay, so thanks.